This final Chapter 7 video looks at the intermolecular forces, the three types, and then it talks about the trends in those intermolecular forces. So to start with, let's look at the types. We've got dispersion forces, which exist between all molecules that have electrons, but they're also the weakest of all the three forces. The next stronger intermolecular force is dipole-dipole forces. So this acts between molecules which are polar. And we talked about polar in a previous video. So if there's a polar bond, for example, HCl is a highly polar bond where the chlorine is more electronegative, then it creates enough of a pole on the molecule there to bond with another one. And lastly, hydrogen bonds, which are again to do with polarity but even stronger. So let's go through each one now. So first of all, we've got dispersion forces. Dispersion forces are made by the electrons as they go around a molecule. You can see here how this molecule has two different nuclei in there. At any one time, the electrons are going to be at one side or another. Just a fact of nature is that if the electron is a single thing, then as it's whizzing around the molecule, if we were to take a snapshot of the molecule at any one time, the electron is one side or the other of the molecule. And because of that, it creates a temporary dipole. And this is a key word, temporary dipole. And because it's temporary, it makes it very weak and momentary. But it is enough to create a small attractive force with the next molecule along. And this is enough to stick substances together a little bit. Now, substances which rely on dispersion forces to hold them together are things like the gases in the air. So things like N2, O2, Cl2. And so they're easily gases at room temperature because the dispersion forces are so weak, it's unable to hold those molecules together. If we look at the trends in these forces, we can look at the halogens, group 17, where we get commonly a diatomic molecule like F2, Cl2, Br2, and I2. And if we look at the boiling point of these, we can see that as we increase the number of electrons in the atom, so iodine is much bigger in terms of electrons and protons, but we're focusing on the electrons, than fluorine is, the boiling point and the melting point too would increase. And that can be explained because with more electrons and further out from the nucleus, iodine has a number more shells than fluorine. So fluorine has 2 shells, whereas iodine has 5 shells. And so the electrons on the outside of an iodine molecule, so obviously we've got 2 of these. Let's just copy paste that. Okay, so that's your iodine there. Okay, versus your that's your fluorine. And so you can see that the electrons are much further away from the nucleus and therefore are able to induce a temporary dipole, more easily. So that's the trend in boiling points there. Also, if we look at the branching of molecules, so this links into hydrocarbons now. If we look at this hydrocarbon on the right, it's branched, whereas on the left it's a straight chain alkane. So when you have these together, the alkanes with the straight chains are able to get much closer together than the branched alkanes. And this close packing actually increases the strength of the dispersion forces between them. So the boiling point is slightly higher, i.e. it requires more energy to boil than the branched alkane. And this has implications for branched alkanes uses. So with fuels, etc., we tend to use branched alkanes for certain fuels and straight chain alkanes for others. for that reason. Okay, moving on to permanent dipoles. So this is where it's no longer a temporary dipole, which is caused by the moving of the electrons. It's now a permanent thing, and it's because of the electronegativity. So see my previous video on polarity to understand that a little bit better. So chlorine is a more electronegative atom than hydrogen, so therefore it's a polar bond. So we can draw that like this to show the dipole on, I'm just doing it for this molecule here. So this is a little symbol to show the dipole, so it's acting in that direction. And what that means is it's a bit like a magnet, but an electrical one, so not north and south, but plus and minus. And it means it's got a little bit of an attractive force that it can help it stick to its neighbouring molecules. So the third one, hydrogen bonding, is where we are looking at the electronegative atoms of fluorine, oxygen, and nitrogen. Or some people just write down NOF because that's the order it appears on the periodic table. Now, if they are attached to a hydrogen, so if you have an NH in your molecule, an OH, or an FH, or HF, what that does is it steals so much of the electron density from the hydrogen that it actually leaves a very positive hydrogen end and a very negative end of that as well. So because of that, this creates almost an ionic bond here, but it basically makes a very, very positive hydrogen. So this is shown in the diagram here. Very, very positive, highly positive. And that is enough to create bonds that go between the hydrogen, which is the positive side, to the negatives of other molecules. So look at this water here. Water is OH, so this is hydrogen bonding. And you can see that the negative and the positive there sticks to the negative, and the positive does the same thing on the other side. So that's called hydrogen bonding. Now, in terms of size, this is about 1/10 the strength of a covalent bond. So it's still not very strong, but it's stronger than the other two. The dipole is about 1/100th of a of a covalent bond, and dispersion is much less than that again. Lastly, we're going to look at what happens when you have lone pairs. So with water, if we focus on what's really occurring here, the hydrogen, which is the positive end, is bonding to the lone pair, which we've looked at as being a sort of sticking out lobe here, and it actually creates a bond with the lone pair. So you can imagine the lone pair sticking out and bonding with the positive hydrogen. So it brings it really close together and really strongly bonds it. Now this is the reason that water is a liquid at room temperature, and most similar molecules would not be. So we're going to look at some examples of those later, but for now we're going to look at how we can show the strength of hydrogen bonding using hydrogen halides. So if we look at hydrogen halides, the only one that does hydrogen bonding is expected to be HF, and we can see that because in the boiling points there's a break in the trends. So normally, as you increase the size of the molecule, you expect the boiling point to go up, and that's because of dispersion forces. So going back to the very first part of this lesson. So for example, H and Cl. Cl has 3 shells, so 1, 2, 3. Okay, so that's H and Cl. Then we've got HBr, so we've got 1 extra shell. Okay, and so on. And so as they go up, dispersion forces is increasing because the electrons can induce a bigger temporary dipole. So dispersion forces increase. And that increases the boiling point. But then hydrogen fluoride should be the lowest, but it's not because of hydrogen bonding. And therefore, the hydrogen bonding for HF is so strong that it actually sticks the substance together to another one with a hydrogen bond, and that makes the boiling point go much higher. So that's a hydrogen bond. And that's why, if you look at hydrogen halides, that's why that occurs. So hydrogen bonding makes that much harder to boil. Okay, that's it for hydrogen bonding. So if you now look at the chapter 7 questions, chapter 7 review, and complete those. Thanks.